All right, so now for the example number 5, we're going to graph these general solutions. And so for example number 5, they give us a differential equation, dy dx is equal to cosine of x. Well, now if I take the derivative of this, if I find the general solution, remember that when they write down the word general, that means that we're going to have some value c. So the general solution is the antiderivative of cosine, which is just sine of x, but it's really a family of functions, so we have to tack on the plus c. They didn't give us an initial value, they didn't give us a value, they didn't ask for a particular solution. So this is the answer, but now what does that look like? How do I graph that? What does that mean? Well, if you go into your graphing calculator, and I already have it entered in, but I wanted to show you this. If I go to L1 and I put in a few values like -3, -2, -1, from -3 to 3, I can plug in L1 into my equation to represent the value of functions. So I'm going to change the order so you know what we're doing. I'm going to go 0, 1, 2, 3, and then I'm going to do -1, -2, -3. Okay? And that way, because I want them to graph the original function first, and that way you can see what it's doing. So now what I'm going to do is I'm going to graph the family of functions. So the general solution is y equals sine of x plus c. Now to graph that, I'm going to clear this out, and I'm just going to put sine of x, but plus c represents any number that I can plug in my calculator. In other words, it's the vertical translation up or down of the function. I'm going to select L1. So if I hit second 1, I can plug in L1. Now what that does for me, and we're going to do a zoom standard, it'll graph the original function sine of x plus 0, which is the first element in list 1, and then it'll do sine of x plus 1, and then it'll do sine of x plus 2, and sine of x plus 3. And what this does is, remember that dy dx represents the slope of the tangent line at any given point. This plus c doesn't change the slope. All those blue lines have the same slope with regards to where they are based on the value of x. In other words, if I were to draw a tangent line right here on this line, on the y-axis, and then I drew another tangent line on the next one, and another tangent line, because I'm vertically shifting the function up, notice that all of those derivatives or all those slopes are the same. Those tangent lines are all parallel. The reason for this is if this is a constant, when I take the derivative of it, this is what I'm left with. So the derivative of all these functions that you see on this graphing calculator are going to be the same, no matter if I shift the graph up or down. So this is going to represent y equals sine of x plus c. Now when we have a plus c, remember that is the general solution. And that's all they're asking us to find right now. And that's how you would represent that on the graph. Now, I'm going to go a little bit ahead and show you guys something else. If I choose to show the slope, remember that the tangent line is the derivative, or let me rephrase that, the derivative of a function. In this case, we're talking about sine of x plus c. The derivative of the function represents the slope of that line at a particular point x. So when x equals 1, if I draw a little line here, and a little line here, and a little line here, tangent to the curve, I get that. If I go to 2, when x equals 2, now my slope changes a little bit. And at 3, it changes a little bit. And these are the tangent lines which represent the slope. And so if I do this for all these values, And I'm going to do a couple more. What I've done is I've just drawn the slope field. And that's what we're learning in this particular section, is how does the slope field apply. So what I've just graphed, if I remove the original function, this is the slope field. And I can evaluate that, or I could graph this by hand two ways. One is I could find the values of dy dx, which is equal to cosine of x, right? So for example, this is 1, 2, 3. That is when x equals 3, my slope has a negative value, right? Does that make sense? Well, now here's an interesting thing. If I come out of the screen here, and it'll be hard to see because I've written over some of this stuff. Let me move that down a little bit so it's out of the way. If I say cosine of 3, and I probably should make sure I'm in radian mode, I get negative 9.8. Well, that represents the slope of the tangent line, so if I come back in here, this slope is negative. When x equals 3, the slope is equal to negative 9 or 0.98. But the slope is really f prime evaluated at 3. Whoops. Okay. So when x equals 3, f prime of 3 is equal to negative 9.8. And so I could take the derivative and evaluate it at x equals 0, x equals 1, x equals, and I could map the slope field, and I can look and see what the original function is. Because if I did the slope field, what does that look like? Well, it's cosine of x. And we'll do that in the next example. So I kind of taught ahead a little bit to help out. Does anybody have any questions about what I've done, though? Right, do you guys understand that when I take the antiderivative of cosine of x, I'm going to get sine of x? But without a point, I don't have a particular solution, I have a general solution, because plus c could have been there. In other words, if I start with sine of x plus 2 and I took the derivative, I would have cosine of x. In other words, if I said sine of x plus 3, what's the derivative of that? Cosine of x. If I said sine of x minus 3, what's the derivative of that? Cosine of x. If I said sine of x minus $1 million, then it's still cosine of x, because the constants c, when I take the derivative, they just go away to 0. Does that make sense? So when we work backwards, we can't ignore them. So we call it a general solution.